Galaxies are drawn together in the vast darkness of space. This process, known as galactic interaction, is the universe's primary method for building its most colossal structures. By the end of this journey, you will understand how these profound encounters forge the giant galaxies that rule the cosmos. We will uncover the invisible forces that orchestrate these unions and reveal the stunning future awaiting our own Milky Way. How does transformation on such a grand scale lead to the emergence of something new and magnificent? The universe is far from a static museum of stars. It is a dynamic arena, a grand web of motion where entire galaxies drift on invisible rivers of force. To truly grasp the concept of galactic interactions, we need to meet the actors in this cosmic play. Galaxies are not all the same. They come in distinct forms, each with its own story and fate. There are majestic spirals like our own Milky Way, with their sweeping arms of stars and gas spinning like great celestial pinwheels. Then there are the irregular galaxies, often shaped by earlier encounters, their forms more free-flowing and unique. And finally, there are the giants, the elliptical galaxies. These are often vast, spherical or egg-shaped collections of ancient stars, holding a different kind of order than their spiral cousins. The stage for their interactions is not empty space. Galaxies are social creatures, often drawn together into massive communities called clusters. Within these dense neighborhoods, the gravitational pull is immense. Think of a crowded ballroom where dancers are constantly nudging and steering one another, their paths forever altered by proximity. This is the environment where the drama of cosmic evolution most frequently unfolds. The gravitational fields of these galaxies are in constant conversation, a silent, relentless tug that sets the scene for the grand mergers that have shaped our universe's history. Understanding this cast of characters and their crowded habitats is the first step to appreciating the powerful, yet profoundly creative, processes that build the giants of the cosmos. Gravity is the silent architect of the cosmos, a force that sculpts the universe on the grandest scales. Imagine two vast ships adrift on a calm, dark ocean. Though they seem motionless at first, each ship creates a subtle dip in the water around it, an invisible influence that draws the other ever closer. In the emptiness of space, this influence is gravity itself. Every galaxy warps the fabric of spacetime around it, creating a profound well that nothing, not even light, can escape. When two of these cosmic islands pass within reach, their mutual pull begins an elegant and transformative dance. Their shapes begin to change, no longer perfect spirals or smooth spheres. Immense streams of stars, gas, and dust are drawn away, stretching out into long, luminous bridges and tails. This beautiful, dynamic process is called tidal stripping, the first gentle step in a celestial courtship. But this dance has a consequence. The galaxies lose energy with every graceful turn, their orbital momentum slowly diminished by interactions with other galaxies or the immense gravity of their home cluster. Like a spiraling funnel, their paths decay, pulling them into an ever-tightening embrace. This persistent, inescapable pull is the fundamental engine of galactic evolution, setting the stage for a far more direct and powerful confrontation that will ultimately forge a new cosmic giant. This slow, inevitable tightening of their orbits is driven by a subtle yet powerful cosmic force known as dynamical friction. Imagine a massive ship moving through a crowded harbor. The water itself, along with all the smaller vessels, creates a gentle but persistent drag on the ship, gradually reducing its forward momentum. In the vastness of space, galaxies experience a remarkably similar effect. As a large galaxy travels through the diffuse sea of stars, dark matter, and even individual star clusters within its companion or its home cluster, it moves through this unseen medium. Each small gravitational influence from these countless invisible particles acts as a gentle brake, a kind of cosmic friction that steadily draws away the galaxy's orbital energy. The outcome is not a sudden impact but a graceful, decaying spiral. The two galaxies begin to circle around their shared center of gravity, but with each beautiful pass, they lose a little more speed, settling ever deeper into the combined gravitational well they have shaped together. This gradual, steady process is the universe's way of making sure that a close encounter is seldom just a brief event. It is the mechanism that guides their cosmic journey, turning a distant gravitational greeting into the beginning of an ultimate and complete union. This initial close encounter is a spectacle of cosmic proportions. Picture two majestic spiral galaxies, each a vast island of billions of stars, beginning to pass through one another. Their elegant disk structures, once stable and symmetrical, are the first to feel the immense and chaotic gravitational pull. These forces warp and twist the galaxies, pulling them into distorted, almost phantom-like shapes. From this gravitational turmoil, vast tidal tails are born. These are luminous rivers of stars, gas, and dust, gently drawn out from their host galaxies. They arc across the void for hundreds of thousands of light years, beautiful and haunting fingerprints of the encounter. It is a paradox of this cosmic meeting that while the stars themselves almost never touch, separated by the profound emptiness of space, the clouds of gas and dust within the galaxies are not so fortunate. These immense cosmic clouds press together with incredible force. This sudden compression triggers the first great wave of intense star formation. The merging system erupts in a brilliant burst of newborn stars, a firework display of cosmic proportions that signals the definitive transition for the original galaxies. But these spectacular fireworks and distorted shapes are just the surface of the event. The true engine of the merger, the force that seals the fate of both galaxies, is something we cannot see at all. The brilliant swirl of stars and glowing gas clouds represents only a tiny fraction of a galaxy's true substance. The vast majority of its mass, perhaps as much as 90%, is locked away in an immense, invisible sphere of dark matter. This mysterious substance does not emit or reflect any light, yet its gravitational influence is absolute. This dark matter halo is the true gravitational anchor of a galaxy, its hidden skeleton. Long before the visible stars begin their intricate dance, these two vast, unseen halos have already started to interact. They act like a form of cosmic glue, their immense gravity entangling the galaxies and ensuring they cannot simply pass through each other and continue on their way. As the merger progresses, these dark matter halos themselves begin to coalesce, swirling together to form a new, larger, and more spherical halo. This invisible process is what ultimately dictates the final structure of the resulting galaxy. The dark matter creates the deep, new gravitational potential well, a foundational bowl of force that will eventually host all the rearranged stars. It is this unseen framework, built from the darkest material in the universe, that fundamentally shapes the outcome of the entire cosmic event from behind the scenes. This sudden, immense compression of interstellar gas clouds ignites a celestial firestorm. The resulting starburst is a cosmic frenzy, a period of star formation so intense it can outshine the entire galaxy. For a brief, spectacular moment, the merging system becomes a beacon of creation, birthing stars at a rate hundreds or even thousands of times faster than a quiet galaxy like our own Milky Way. These are not ordinary stars. Many are colossal giants burning fiercely and living fast. Their intense radiation floods the system, but to our eyes, much of this light is hidden. The collision stirs up vast clouds of dust, a fine cosmic material that absorbs the brilliant starlight and glows warmly, re-radiating the energy as a profound infrared glow. This is why many of the universe's brightest infrared objects are not single stars, but these merging starburst galaxies, their brilliant light transformed by the material of the collision. Yet, such a powerful burst of activity cannot last. This incredible display rapidly consumes the very gas that fuels it. Like a brilliant event that uses all its available resources, the starburst phase is spectacular but short-lived. It leaves behind a galactic system now rich in new stars, but critically poor in the cold gas needed to form the next generation. This transition is a pivotal step, a fundamental change that guides the future of the newborn galaxy toward a very different destiny. Deep within the heart of this cosmic collision, another, more profound drama is unfolding. At the center of nearly every large galaxy, including our Milky Way, resides a supermassive black hole, a gravitational singularity of almost unimaginable density. When two galaxies merge, these two immense entities are carried along with the flow of stars and dark matter, inevitably drawn toward the very core of the new, combined galaxy. There, they find themselves locked in a gravitational embrace, beginning an orbital dance of titans. Initially, they form a binary pair, two cosmic heavyweights circling one another in a slow, majestic waltz set to the rhythm of gravity itself. This dance is not performed in isolation. As they orbit, their immense gravity sends nearby stars away into the darkness, a process that steadily drains their orbital energy. With every star cast out, the black holes lose a little more momentum, spiraling ever closer together over millions of years. This long, slow cosmic choreography is a prelude to a final act of incredible power. The theory of general relativity predicts that their ultimate union would release an immense burst of gravitational waves, powerful ripples in the very fabric of space-time that would spread out across the entire universe. But the collision does more than just create these invisible waves. The same chaotic forces that trigger the starburst also channel enormous amounts of gas directly toward the newly forming binary system. This sudden influx of fuel can awaken the merged black hole, transforming it into an active galactic nucleus, a beacon of radiation so intense it can outshine every single star in the galaxy combined. This brilliant, fleeting outburst is the final, spectacular signature of the galactic union, a last flash of cosmic fire before the new giant settles into its long, quiet future. The brilliant chaos of the merger eventually settles, leaving behind a fundamentally new kind of object. The elegant, spinning disks of the original spiral galaxies are gone, reshaped by immense gravitational forces. In their place stands a smooth, almost cloud-like collection of ancient stars, a giant elliptical galaxy. This transformation is the final, defining step in the creation of a cosmic giant. The process that achieves this is known as dynamic relaxation, a term that captures the profound rearrangement of the galactic system. During the merger, the gravitational field fluctuates widely, a shifting sea of powerful influences. This motion completely reorders the once predictable paths of billions of stars. Instead of circling in a flat plane like cars on a racetrack, their journeys are scattered in every conceivable direction, creating a vast three-dimensional swarm. The result is that characteristic round or oval shape, a structure without spiral arms or a distinct disk. This new galaxy is also a much calmer place. The tremendous period of star formation and the activity around the central black hole have used up or cleared away nearly all the remaining cold gas, the essential material for new stars. Without this resource, the galaxy can no longer form a new disk or spark significant stellar birth. Its stellar population ages together, growing older and redder. This is why the most massive galaxies we observe throughout the universe are almost always these elliptical giants. They are the ultimate products of cosmic mergers, vast stellar systems shaped and settled by the most energetic and creative events the universe can provide. These calm elliptical giants are not always the final stop in a galaxy's evolution. Within the most crowded neighborhoods of the universe, an even more dominant force is at work. Galaxy clusters are the ultimate arenas for a process we might call galactic integration. At the very heart of these dense cosmic cities, a singular behemoth often resides, a type of galaxy known as a CD galaxy. This is not a product of a single, dramatic merger between two equals. Instead, this central giant grows through a more relentless and continuous form of growth. Its immense gravitational presence acts like a deep well at the center of the cluster. Smaller satellite galaxies orbiting through this dense region can stray too close to this overwhelming force. When they do, they are gently drawn into its influence. The central giant's gravity gradually reshapes these smaller systems, stretching them into long, faint streams of stars that are eventually incorporated, adding to the giant's own immense and diffuse halo. This is a slow, steady process of accumulation that unfolds over billions of years. It allows the CD galaxy to become orders of magnitude more massive than our own Milky Way, a true cosmic sovereign that dominates the cluster's center. Its sheer size and the history written in its faint outer halo serve as a lasting fossil record, a silent testament to the cluster's long and dynamic story of growth and integration. Yet within this grand cycle of consumption, a remarkable act of creation is also taking place. The very forces that pull galaxies apart can also build new worlds from what is left behind. Those immense luminous tails of stars and gas stretched across space are more than just scattered material. They are stellar nurseries on a truly epic scale. The vast clouds of gas within these tidal tails, once stable within their home galaxies, are suddenly compressed and set adrift. Out in the relative quiet of intergalactic space, they can collapse under their own weight. These collapsing clouds ignite with new stars, and sometimes they gather enough material to form their own self-contained, gravitationally bound systems. The result is a tidal dwarf galaxy, a brand new, small, and irregular island of stars born directly from the material of its colossal parents. This is a profound cosmic paradox, where the transformative process of a galactic merger directly seeds the birth of entirely new galactic entities. These tidal dwarfs are fundamentally different from the galaxies that created them. They form from the recycled gas and stars of the interaction, material already enriched with heavy elements from earlier generations of stars. More intriguingly, they seem to lack the massive dark matter halos that anchor primordial galaxies. Their gravity and structure are dominated by the visible matter from which they were born. This makes them unique natural laboratories for understanding how galaxies can form without the dominant influence of dark matter. Their very existence is a beautiful testament to the universe's cyclical nature, a constant dance where transitions and new starts are forever intertwined. While we cannot witness a single galactic merger from beginning to end, we have a powerful tool to visualize these epic events. Supercomputers allow us to construct entire virtual universes governed by the precise laws of physics. Cosmologists input the fundamental rules of gravity, the flow of gases, and the recipes for star formation into these digital laboratories. Then they set the simulation in motion, watching as two spiral galaxies, defined only by lines of code, begin their gravitational dance. Over millions of simulated years, we see the entire process unfold in a matter of hours. The elegant disks warp and twist, luminous tidal tails stretch out into the digital void. A brilliant firestorm of new stars ignites within the compressed gas, and finally, the chaotic swirl settles into the smooth, round form of an elliptical giant. These simulations are more than just spectacular visualizations. They provide a crucial test for our theories. When the patterns generated by the computer, the specific shapes of the tidal tails and the timing of the starbursts match exactly what we observe with our telescopes in distant, merging galaxies, we receive powerful confirmation. This remarkable agreement between digital prediction and cosmic reality gives us tremendous confidence that we are truly understanding the fundamental forces that build the largest structures in our universe. The universe itself provides the most compelling testimony for this grand story of creation and connection. We are not merely interpreting ancient light, we are reading a cosmic fossil record written in the shapes and motions of galaxies. Our most powerful telescopes act as time machines, capturing snapshots of this immense process frozen at different stages. In some images, we find galaxies with double nuclei, two bright hearts still beating separately within a single, distorted body. This is the unmistakable signature of a partnership in progress, a celestial union not yet fully complete. Then there are the truly iconic systems, like the spectacular antennae galaxies. Here we see two spirals locked in a tight, dynamic embrace, their long tidal tails of ejected stars streaming outward like the antennae of some vast cosmic insect. This is the starburst phase made visible, a brilliant firestorm of newborn stars illuminating the colossal interaction. But the evidence is not only found in these dramatic, ongoing events. Look closer at the calm, smooth giants, the elderly elliptical galaxies that should be the quietest of all. Within their faint outer halos, astronomers can detect delicate shells and ripples, like the concentric rings on the surface of a pond long after a stone has fallen in. These are the preserved imprints of past encounters, the final, fading echoes of smaller galaxies that were integrated long ago. The proof goes even deeper than shape. By analyzing the subtle motions and chemical compositions of the stars within these giants, we can perform a kind of galactic archaeology. The stars retain a memory of their origin. Astronomers can identify distinct stellar populations, groups of stars with ages and chemical signatures that are completely different from their neighbors. This is the direct chemical evidence of cosmic assembly, the undeniable sign that the giant we see today was formed from the contributions of multiple, unique galaxies in the distant past. The evidence for this cosmic assembly is written in starlight. Look toward the constellation of Virgo, and you will find a perfect specimen, the giant elliptical galaxy known as Messier 87. Residing at the very heart of the Virgo cluster, M87 is not merely a large galaxy, it is a cosmic integrator of almost unimaginable scale. Its calm, smooth appearance belies a long history of steady growth. How can we be so sure? The proof is in the faint, surrounding glow. M87 is enveloped by a vast, diffuse halo of stars, a celestial shroud that stretches far beyond its bright core. This halo is not a natural part of a single galaxy's birth. Instead, it is the accumulated material, the lasting signature of countless smaller galaxies that were drawn in by its overwhelming gravity over billions of years. Each incoming system has contributed its stars to this immense cloud, a permanent record of the galaxy's expansive growth. Further evidence comes from the sheer number of globular clusters, dense spherical collections of ancient stars that orbit the galaxy like a swarm of cosmic bees. A typical galaxy the size of the Milky Way might have 150 of these clusters. M87, however, is surrounded by thousands. This incredible population is far more than it could have formed on its own. These clusters are the inherited possessions of the many galaxies it has welcomed, each smaller system contributing its own family of clusters to the giant's growing treasury. This process of steady accumulation has not only built the galaxy's stellar body, but has also fed the true engine at its core. The first ever image of a black hole, that iconic orange ring captured by the Event Horizon Telescope, was of the supermassive black hole at the center of M87. This black hole is a true behemoth containing the mass of billions of suns. Its immense size is not a coincidence. It is the direct product of the galaxy's long history of integration, a gravitational anchor that has grown through absorbing both gas and the central black holes of all the galaxies it has merged with over the eons. Messier 87 stands as a prime specimen, a finished product that shows us the ultimate destiny of a cosmic giant built through relentless unification. The scale of a galactic merger dictates its ultimate outcome. We can think of these cosmic encounters as falling into two distinct categories, a division between gentle assimilation and total transformation. A major merger is the universe's most dramatic restructuring event. This occurs when two galaxies of roughly similar size, such as two majestic spiral galaxies, come together. The gravitational forces involved are so immense that neither participant can retain its original form. Their structures are completely reshaped, their stars scattered into new, randomized orbits, ultimately forging a brand new type of galaxy, the smooth, featureless elliptical. This is a true rebirth, a powerful and creative event that leaves the original spirals fully transformed. In stark contrast stands the minor merger, a far more common and subtle process. This is the gentle consumption of a dwarf galaxy by a much larger neighbor. The difference in scale is profound, like a great whale absorbing a small school of fish. The gravitational influence of the small companion is simply not enough to disrupt the overall disk and spiral structure of the giant. The larger galaxy remains recognizably itself, its fundamental shape preserved. Yet, the encounter is not without effect. The incoming dwarf galaxy is gradually drawn out by tidal forces, its stars carefully redistributed and added to the large galaxy's faint outer stellar halo. This process also imparts a subtle jostling, a gentle gravitational stirring that slightly warms the larger galaxy's disk, making it just a bit thicker and puffier over billions of years. Our own cosmic home is a living testament to this gentler form of growth. The Milky Way is not a static island, it is a dynamic system currently engaged in several minor mergers. Right now, streams of stars from the Sagittarius dwarf spheroidal galaxy are being woven into the fabric of our galaxy's halo. This ongoing assimilation is a quiet but continuous form of cosmic maintenance, a process that steadily contributes new stars and builds up our galaxy's extended structure without triggering a dramatic transformation. It is a reminder that even in the absence of major collisions, galaxies are never truly finished growing. They are constantly evolving through these quiet, persistent acts of integration. Our own galactic home is not an exception to this universal rule. The Milky Way and its closest giant neighbor, the Andromeda Galaxy, are locked in a mutual gravitational embrace, two dancers on a course set billions of years ago. They are racing toward one another at a breathtaking speed of about 110 kilometers every single second. While the time scales are almost beyond human comprehension, the outcome is a near certainty. In roughly 4.5 billion years, these two great spirals will begin their first dramatic close encounter. This will not be an instantaneous crash, but a prolonged and intricate gravitational ballet that will unfold over another 2 billion years. The two galaxies will swing past each other, their gravitational forces warping their classic spiral shapes beyond recognition. Vast tidal tails of stars, gas, and dust will be pulled out, stretching across the emerging system. The sky from any future Earth-like world would become an ever-changing tapestry of cosmic chaos and creation, with the structure of the familiar Milky Way completely rewritten night after night. Throughout this long process, the compression of immense gas clouds will ignite furious waves of new star formation, briefly turning the merging pair into a brilliant starburst. Yet, this period of intense creativity will also consume the raw materials needed for future generations of stars. The elegant disks of both galaxies will be irrevocably scrambled. Their stars, once traveling on orderly circular orbits, will be scattered into a chaotic, three-dimensional swarm. The final result of this billion-year-long transformation will be a single, vast, and smooth elliptical galaxy. Astronomers have already given this future giant a name, Milky-Way. This predicted future provides a profound perspective, connecting the distant cosmic processes we observe across the universe directly to our own celestial backyard. It demonstrates that we are not merely observers of this grand cycle, but active participants in the ongoing evolution of the cosmos. This cosmic collision, which reshapes entire galaxies, also reaches down to touch the fate of individual worlds. For a planetary system like our own, navigating a galactic merger would be a journey through a transformed and more dynamic environment. The serene stability we take for granted would be replaced by a sky filled with new possibilities and challenges. The most immediate change would be a dramatic increase in stellar density. As the two galaxies intermingle, the number of stars in any given volume of space rises significantly. This naturally increases the probability, however small, that another star could pass relatively close to our solar system, while the average distances between stars are still immense, making an actual collision between planetary systems almost unthinkable. A near encounter is a different kind of consideration. A passing star's gravity would act like a subtle hand, reaching into the distant, icy reservoir of comets that surrounds our Sun, the Oort cloud. Such a gravitational nudge could dislodge countless comets, sending them on new trajectories sunward. This could trigger a prolonged period of cometary activity in the inner solar system, altering the environment for planets like Earth. The cosmic transformation in the galaxy would be mirrored by a potential increase in celestial activity right here at home. Beyond this gravitational influence lies an even more pervasive consideration: radiation. The merger's most energetic phases flood the galaxy with intense light. The brilliant starburst birthing countless massive stars and the awakened supermassive black hole, an active galactic nucleus, both become powerful sources of high-energy radiation. This cosmic glow could affect planetary atmospheres and expose surfaces to levels of energy that would challenge life as we know it. For any emerging biology, this period would represent a profound transition, a test of resilience that could reshape worlds across the newly forming galaxy. Yet within this dynamic change lies a profound and essential creativity. The very same supernova that are a powerful force in the starburst are also cosmic forges. They blast out newly created heavy elements, the atoms of iron, oxygen, silicon, and carbon that are the fundamental building blocks of rocky planets and the chemistry of life. The merger churns the galactic medium, spreading these enriched materials far and wide, seeding future generations of stars and planets with the raw ingredients for a more complex existence. This is the ultimate paradox of the galactic merger. a process that simultaneously presents existing worlds with change while meticulously preparing the cosmic inventory for new ones. It is a cycle of transformation and creation woven together, ensuring that the universe's grandest events touch everything, from the largest galaxy to the smallest, most promising speck of dust that might one day become a world. The final form of a merged galaxy is profoundly shaped by a single, crucial ingredient: the amount of cold gas it contains. This invisible resource acts as the primary fuel for cosmic creation, and its abundance or absence at the moment of collision dictates the entire character of the event. When two gas-rich spiral galaxies meet, they are not just collections of stars coming together, they are immense reservoirs of potential. The interaction strongly compresses these vast clouds of gas, igniting the brilliant, furious starbursts that define the most spectacular mergers. This is what astronomers call a wet merger, a term that vividly captures the presence of this essential, fluid-like material. The resulting firestorm not only forges new stars at a staggering rate, but also rapidly consumes the very gas that powers it. This intense activity ultimately helps to settle the new galaxy into its final, calm state as a massive elliptical, a system now largely without the cold gas needed for future star formation. But what happens when two galaxies have already used up their fuel? Consider two elderly elliptical galaxies, often described as red and quiet because their star-forming days are long over. They are composed almost entirely of ancient, aging stars with very little cold gas remaining between them. When these cosmic seniors merge, the process is strikingly different. This is a dry merger, a quiet and largely dark union. Without a significant gas reservoir, there is no strong compression, no brilliant starburst, and no wave of new stars. The event is a more straightforward gravitational combination. The stars from both systems are gently mixed into a new, larger swarm, resulting in a bigger, more massive elliptical galaxy, but one that is just as calm and red as its predecessors. It is a simple addition of stellar populations, a growth in size without the fireworks of rebirth. This fundamental distinction between wet and dry mergers helps explain the rich diversity we see among the giant elliptical galaxies that dominate the cores of galaxy clusters. Some of these giants show subtle signs of recent, quieter activity or possess specific chemical signatures that hint at a more energetic, gas-fueled origin in the distant past. Others appear to be the pristine products of a series of dry, orderly unions, their stellar populations uniformly old and calm. By reading these clues, astronomers can peer back in time, linking the present-day state of a colossal galaxy directly to the specific conditions of its assembly billions of years ago. The story of its birth, whether it was a fiery, wet creation or a calm, dry accumulation, is permanently written into its stars. This grand cycle of creation and consumption has not always unfolded at the same pace. The universe had a far more active and formative youth. In its earliest epochs, the cosmos was a much denser place, with galaxies packed closer together, like a crowded room in its first moments. This proximity made gravitational encounters, close passes, and full-scale mergers a frequent and dominant feature of cosmic life. The evidence for this dynamic past is written across the deep sky. When astronomers point our most powerful telescopes, like the Hubble Space Telescope, at a single, seemingly empty patch of darkness for days on end, they capture an image known as the Hubble Ultra-Deep Field. This iconic view is not a photograph of nearby grandeur, but a core sample drilled deep into cosmic time. It reveals thousands of the most distant galaxies ever seen, each a tiny, faint smudge of light that has traveled for billions of years to reach us. And within this ancient crowd, a striking pattern emerges. A significant fraction of these primordial galaxies show clear signs of transformation. Their shapes are often distorted, stretched, and pulled. Many appear as irregular forms or chain-like structures caught in the very act of merging. They are not the neat, defined spirals and ellipticals we see in the modern universe, but galaxies still under construction, their final forms being shaped through frequent encounters. As the universe has aged, this active pace of interaction has steadily slowed. The relentless expansion of space itself has been the great calming influence. Over billions of years, the average distance between galaxies has increased, stretching the cosmic fabric and spreading out the celestial population. With more space between them, the chances of a close encounter have diminished dramatically. In our present cosmic era, for a galaxy much like our own Milky Way, a major merger is a relatively rare event. Current observations suggest that only a few % of such galaxies are currently undergoing a significant, transformative collision. For most, the dominant mode of growth has shifted to the quieter, more gradual process of minor mergers, the steady accretion of tiny dwarf satellites. Yet, even today, the merger engine has not completely shut down. It simply operates with renewed vigor in specific, crowded environments. At the hearts of massive galaxy clusters, where hundreds or thousands of galaxies are drawn together by immense gravity, the conditions remain ripe for interaction. In these dense cosmic cities, the merger rate is sustained at a higher level, a persistent hum of activity that continues to build the most massive central galaxies through both dramatic unions and gentle assimilation. Understanding this changing rate, from the frequent encounters of the early universe to the more measured growth of the present day, is absolutely vital. It is the key to building accurate models of galactic evolution. By charting how often mergers occurred across cosmic time, cosmologists can run the universe's history in reverse, piecing together the precise sequence of assembly that built the rich and varied population of galaxies we observe across the cosmos today. Sometimes the most dramatic cosmic encounters give rise to the gentlest of giants. The universe's appetite for galactic transformation can produce results that defy our expectations, leading to the creation of some of the most enigmatic objects we have ever observed. These are the ultra-diffuse galaxies, vast cosmic phantoms that challenge the very definition of what a galaxy can be. Picture an island of stars as wide as our entire Milky Way, but one that holds only 1,000th of the stars. Its stellar population is so sparse, its light so faint, that it barely registers against the blackness of space. These are not the brilliant spirals or dense ellipticals we are familiar with. They are cosmic will-o'-the-wisps, enormous yet almost invisible. How does such a ghostly structure emerge from the same powerful processes that build the universe's most colossal giants? The answer appears to lie in a specific and transformative sequence of events, a celestial preparation that occurs within the crowded confines of a galaxy cluster. When a typical spiral galaxy, rich with gas and stars, first falls into one of these dense cosmic communities, it meets a formidable and invisible force. The space between galaxies in a cluster is not a perfect vacuum. It is filled with a searingly hot, thin plasma known as the intracluster medium. As the spiral galaxy moves through this superheated gas at immense speeds, it experiences a phenomenon called ram pressure stripping. Think of a car driving at high speed through a heavy downpour. The rain does not fall gently on the windshield. It is pressed flat against the glass by the force of the vehicle's motion. In a similar way, the pressure from the intracluster medium acts like a powerful cosmic wind, gently but firmly pushing the spiral's own cold gas reservoir out of the galaxy and leaving it behind in a long, trailing tail. This process effectively starves the galaxy, removing the very fuel it needs to form new stars. What remains is a gas-poor, quiescent system, a galaxy that has been pre-processed, its most vital resource drawn away before the main event even begins. This prepared galaxy, now more exposed, is then set on a new course. When it finally undergoes a merger with another galaxy, the encounter unfolds very differently than a typical gas-rich union. Without a significant reservoir of cold gas, there is no brilliant starburst, no firestorm of new stars to light up the proceedings. The merger is a quiet, dark, and fundamentally gravitational affair. The gravitational forces of the interaction act on this pre-processed system, stirring its remaining stars, but with no dense gas to anchor them or to form new, bright structures. The stars are simply scattered into a much larger volume of space. The entire system is puffed up, stretched out into a vast, incredibly diffuse cloud. The result is an ultra-diffuse galaxy, a celestial paradox that is both immense and faint. The discovery and study of these ghostly giants forces us to reconsider our traditional models of galaxy formation. They are a powerful reminder that the process of galactic evolution is not a single, predictable assembly line. It is a complex and creative chain of events, sensitive to initial conditions and environment. A galaxy can be reshaped, stirred, and transformed into something entirely unexpected. A quiet, sprawling testament to the surprising variety of forms that the cosmos can sculpt. These galactic collisions are far more than architectural events. They are the universe's primary foundries, forging the very elements that make our world possible. The furious starbursts ignited during a merger do not just create stars, they create a specific kind of star. The immense compression of gas clouds favors the birth of colossal, brilliant, but tragically short-lived stellar giants. These massive stars burn through their nuclear fuel in only a few million years, a mere blink in cosmic time, before ending their lives in spectacular supernova events. It is within these titanic blasts that the true alchemy occurs. The intense heat and pressure fuse simple atoms into heavier elements, transforming primordial hydrogen and helium into the building blocks of complexity. Oxygen, carbon, iron, silicon, all the atoms that form rocky planets, the air we breathe, and the very molecules of life are forged in these stellar infernos and then scattered outward into the surrounding gas clouds. A single merger event can trigger countless such explosions, enriching the galactic system with a newly formed cocktail of heavy elements. This process, repeated across countless galaxies and mergers over billions of years, has steadily raised the chemical richness of the cosmos from the simple beginnings of the Big Bang to the complex periodic table we know today. The iron in our blood and the calcium in our bones were once created in the heart of a massive star, born from a galactic collision that occurred long before our solar system even existed. But the influence of these cosmic factories does not stop at the galaxy's edge. The combined energy from supernova and radiation from the starburst itself can generate immense pressure, driving powerful galactic winds. These winds act like a cosmic bellows, pushing the newly enriched material, this gas now rich with complex atoms, out of the galaxy entirely and into the vast intergalactic voids. There, this chemically advanced material mixes with the pristine hydrogen gas that has remained untouched since the dawn of time. When this enriched gas eventually cools and collapses to form a new generation of galaxies or stars, it does so with a head start. It already contains the seeds for rocky planets and the potential for chemistry far more intricate than would otherwise be possible. This means that the act of one galaxy interacting with another does not just reshape their mutual structure. It seeds the entire cosmic environment with the prerequisites for complexity. The grand cycle of galactic interaction is paradoxically a fundamental act of creation. responsible for distributing the essential ingredients for planets and perhaps even life across the vast expanses of the universe. Even a galaxy that appears perfectly calm can betray a turbulent past. The challenge for astronomers is to read the subtle signatures of a merger long after the final star has settled into its new orbit. Unraveling the history of a quiet-looking elliptical galaxy is a form of cosmic archaeology, where the evidence is not preserved in stone but written in starlight and motion. One of the most telling clues is the presence of faint concentric shells or ripples that envelop the galaxy's smooth core. These are not made of gas but of stars themselves, arranged in vast, delicate arcs. They are the last fading echoes of the immense tidal forces that once reshaped the galaxy, the final, slow-moving waves from a union that occurred billions of years ago. Another method involves studying the kinematics, the precise movements of the stars within the galaxy. If all the stars were born in the same place and time, their orbits would be relatively simple and uniform. But in many ellipticals, astronomers find complex, interwoven streams of stars moving in different directions, or even counter-rotating components where one group of stars orbits backward relative to another. This intricate orbital ballet is incredibly difficult to explain through a single, monolithic collapse. It is far more consistent with the idea of multiple systems, each with its own original spin, being stirred together into one new galaxy. The evidence can also be found by looking at the galaxy's most extreme features. The presence of a central supermassive black hole that is disproportionately massive for the size of its host galaxy points to a history of galactic integration. This colossal anchor likely grew by merging with the black holes of other galaxies, each union adding to its immense gravity. Similarly, an unusually large population of globular clusters, those dense swarms of ancient stars, can act as a fossil record. A galaxy that has thousands of these clusters, like Messier 87, almost certainly gathered most of them from the smaller galaxies it joined with over time. Each of these faint clues, from the gentle shells of stars to the complex motions within, tells a story. They are the lasting imprints of a dramatic, creative event that transformed separate islands of stars into a single cosmic giant. This relentless cycle of growth and consumption is held in check by a powerful, self-regulating system. The very forces that signal a galactic merger also contain the mechanisms to limit its ultimate scope. The brilliant starbursts and the flaring active galactic nucleus are not just spectacular side effects, they are powerful governors. These events unleash a phenomenal amount of energy, flooding the galactic environment with intense radiation and shock waves from countless supernovae. This energy does not simply fade away, it acts upon the galaxy's remaining gas reservoir. The interstellar medium is heated to extreme temperatures, making it far too energetic to collapse and form new stars. In more dynamic cases, this energy translates into motion, driving vast galactic winds that can push the gas itself right out of the galaxy, sending it into the emptiness of intergalactic space. This process creates a profound and self-imposed limitation. By releasing its own star-forming fuel, the galaxy effectively puts itself on a cosmic diet. The furious burst of creation consumes the available resources and then actively removes the possibility of a repeat performance. This same feedback also regulates the growth of the central supermassive black hole. The energetic output from the active galactic nucleus can heat or push away the very clouds of gas that are flowing in to sustain it, essentially cutting off its own supply. This prevents the black hole from growing to an unimaginably large size and helps explain why we do not see galaxies with central black holes that have consumed their entire host. This concept of feedback is not just a theoretical idea. It is a critical ingredient that makes our models of the universe work. When cosmologists include these self-regulating processes in their supercomputer simulations, the virtual universe that emerges looks remarkably like the one we see through our telescopes. It produces a realistic mix of galaxy types and sizes, from active, star-forming spirals to quiet, red ellipticals. Without this built-in balancing act, the simulations tend to create galaxies that are far too massive and too bright, failing to match the observed cosmic landscape. This delicate interplay between growth and regulation is what allows for the stable, long-term evolution of galaxies, ensuring that the universe builds its giants without letting them overwhelm everything in their path. To find the origin of these cosmic giants, we must journey back to the very dawn of time. The James Webb Space Telescope is our most powerful window into this ancient era, a period known as the epoch of reionization. This was the universe's formative age, a time when the first light began to pierce a primordial fog of neutral hydrogen. What the telescope is finding there is rewriting our cosmic history books. It is capturing the faint glow of the very first galaxies, not as the majestic spirals or ellipticals we know today, but as tiny, fragile seeds. These infant systems were much smaller and more chaotic than their modern descendants, glowing fiercely with the light of their first massive stars. One of the telescope's most profound missions is to witness the initial moments when these primordial building blocks began to coalesce. We are now seeing the faint, distorted shapes of the very first galactic mergers, the foundational acts of assembly that set the entire cycle of cosmic evolution in motion. By studying these ancient encounters, we can answer one of astronomy's greatest questions. How did the first supermassive black holes, those gravitational anchors at the heart of nearly every large galaxy, form so quickly after the Big Bang? The leading theory suggests that the dense, gas-rich conditions within these early mergers provided the perfect nursery. Collapsing gas clouds could have directly formed massive black hole seeds, which then grew rapidly by drawing in the abundant surrounding material and by combining with each other as their host galaxies merged. This process, witnessed in its infancy by the telescope, shows us how the earliest ancestors of elliptical galaxies began to take shape. These were not the calm, red giants of today, but blazing, compact objects, furiously forming stars and growing their central black holes in tandem. This research pushes at the very frontier of our knowledge, revealing how the fundamental recipe for building a galaxy, the integration of smaller systems by larger ones, was established when the cosmos was in its youth. Every colossal galaxy we see around us today, including our own Milky Way, contains the legacy of those first, modest mergers that began over 13 billion years ago. This relentless cosmic process invites us to reconsider our own place in the universe. We are not living in a finished, permanent creation, but within a dynamic and evolving system that builds its largest structures through a hierarchy of mergers, from the tiniest star clusters to the mightiest galactic giants. Our very existence is a direct product of this grand cycle. Every atom of iron in your blood, every particle of oxygen you breathe, was forged in the heart of a massive star. Many of those stars were likely born during the intense starbursts of ancient galactic encounters, their brief, brilliant lives enriching the cosmos with the heavy elements necessary for planets and life itself. We are, in a very real sense, made from the legacy of these cosmic events. The knowledge that our own Milky Way is destined to merge with the Andromeda galaxy further weaves our story into this vast tapestry. It places our fleeting human lives within a narrative that spans billions of years, connecting our moment of conscious awareness to the epic cycles of galactic evolution. This perspective challenges our deep-seated perception of a stable, unchanging heavens. It reveals that change on the most profound scales imaginable is not an exception but the fundamental law of the cosmos. Our world, our sun, and our galaxy are all transient participants in an endless dance of transformation, reminding us that we are both witnesses to and products of the universe's creative, ongoing power. From the silent, invisible pull of dark matter to the brilliant firestorms of colliding gas, the story of galactic encounters is one of profound transformation. This cosmic process is far more than a tale of change. It is the universe's primary method for forging its grandest structures and for enriching the void with the very ingredients of complexity. Our journey through these celestial meetings reveals a cosmos built not on permanence, but on a beautiful, relentless cycle of renewal. Gravity is the great architect, and its blueprints are written in the language of interaction and integration. We have seen how this process, observed through our most powerful telescopes and confirmed by intricate computer simulations, shapes everything from the faintest dwarf galaxy to the most colossal elliptical giant. It is a narrative that connects the ancient past, witnessed by the James Webb Space Telescope, to the distant future of our own Milky Way's inevitable union with Andromeda. These mergers are the fundamental engines of cosmic evolution, responsible for building the massive galaxies that anchor the universe and for seeding the interstellar medium with the heavy elements that form planets and enable life. As Carl Sagan so eloquently reminded us, somewhere, something incredible is waiting to be known. The ongoing story of how galaxies interact to create cosmic giants is one of those incredible truths, a testament to the dynamic and creative power of the universe. If this exploration of the cosmos has expanded your mind, please subscribe for more journeys into the mysteries of space and share your thoughts on this epic process in the comments below.